Welcome students, welcome to our new section Reciprocating Air Compressor Part 7. Today we will be deriving the formula for calculating the minimum work required for a two-stage reciprocating air compressor. In the previous lecture we derived the formula for calculating the work done. Here we are going to derive the formula for calculating the minimum work in case of two-stage reciprocating air compressor with perfect intercooling. The first formula in the given slide represents the formula for two-stage compression with perfect intercooling. Now, when you observe this equation, we can find that all other terms except P2 is varying. So is constant. Only P2 is the varying quantity in this equation. You can see it also from the figure. This shows the PV diagram for a two-stage reciprocating air compressor. Here the shaded region or the shaded area gives the amount of work which is saved as a result of two-stage compression. Here you can see from the figure, as P2 tends to P1, the is area varies, and as P2 tends to P5, when P2 tends to P5, this area varies. So you know that P2 is a varying quantity and it depends upon the value of P2, the work will be minimum or maximum. So for obtaining the maximum work, we differentiate the above equation and equate it to 0. Why we need to differentiate and equate it to 0? Because this is nothing but the slope of the curve. You know that here we need to find the minimum work, right? At minimum point, the slope will be 0. So that's for maximum point also the slope will be 0. For getting maximum point and minimum point, we differentiate the varying quantity and equate that term to 0. So here we are going to substitute the value of W from here and substitute it in the second equation. For simplification, we put n divided by n minus 1, which is a constant, as Z. So here in place of n divided by n minus 1, we substitute it. We replace that with Z. Here also we replace with Z. Here also we replace it with Z. So the equation will become Z P1 V1 P3 divided by P2 the whole raised to Z, P2 divided by P1 the whole raised to Z. You can clearly see that the varying quantity is P3 divided by P2 the whole raised to Z and P2 divided by P1 the whole raised to Z. All the quantities are constant. So take that quantities out and differentiate with respect to P2 and equate to 0. Before that, you need to understand what is integral x raised to n. So x raised to n plus 1 divided by n plus 1. And what is the derivative of integral x raised to n? N into x raised to n minus 1. I think all of you know this formula. So we can use this identity for derivating the given expression. Here, since we are differentiating with respect to P2, P3 is the term which is constant. So P3 raised to Z, I put it like this, and 1 divided by P2 raised to Z, I can put it as P2 raised to minus Z. Then I can use the identity x raised to n, that is minus Z, that is n into x raised to n minus 1. So it will become P3 raised to Z into minus Z, P2 raised to minus Z minus 1. Then that plus. Then P2 the whole raised to Z, and after differentiation I can put it as Z P2 raised to Z minus 1. And 1 divided by P1 raised to Z is constant, so I can write it as P1 raised to minus Z. Since this term contains a minus sign, So I will bring that term to the right hand side. So the equation becomes P3 raised to Z, P2 raised to minus Z minus 1 is equal to P1 raised to minus Z into P2 raised to Z minus 1. Then I cancel this Z term and this Z term. So I got an equation. I bring this P2 raised to minus Z to minus 1 to the right hand side. So this will be like here, this, and I bring this P2 raised to minus Z minus 1 to the right hand side, and I will bring this to this side. So when this equation I can write as P2 raised to Z minus 1 into P2 raised to Z plus 1, and this equation I can write it as P3 raised to Z into P1 raised to Z, right? So x raised to n into x raised to m, x raised to n plus m. So when I use that identity, this will become P2 raised to 2Z and P3Z into P1Z. I can write this. When I cancel these Z and Z terms, I got an equation like P2 square is equal to P3 into P1. So this value of P2, when you substitute this value of P2 in the work equation, you will get the minimum work. Before substituting, I will rearrange this equation like these two. That is, this equation, when cross multiply it, we will get the same first equation, that is P2 into P2, P2 square, P3 into P1. Right. So this equation, after dividing it with P1, these two equations after dividing with P1, I can get an equation like this. P2 divided by P1 is equal to P3 divided by P1 the whole raised to 1 by 2. So P2 divided by P1 is equal to P3 divided by P2 is equal to root of P3 divided by P1. So this equation I can rearrange it into these two equations. So I have the formula for work done. In this equation there is P3 divided by P2. I replace this P3 divided by P2 with P2 divided by P1. So the equation will become like this. When I take P2 divided by P1 and n minus 1 common, I can write it as 2 P2 divided by P1 the whole is n minus 1 minus 2. When I took 2 common from this, it will become 2n divided by n minus 1 P1 V1 into P2 divided by P1 the whole raised to n minus 1 by n minus 1. So this is the formula for calculating the minimum work for a two-stage reciprocating air compressor with perfect intercooling. So you know the formula, and you have one more. When you rearrange that equation, you get one more equation like this. In this equation there is P2 divided by P1. So use the first term and the second term and replace this term with P3 divided by P1 the whole raised to 1 by 2. You will get an equation like this: 2n divided by n minus 1 P1 V1 into P3 divided by P1 the whole raised to n minus 1 divided by 2n minus 1. So these formulas you need to by heart for doing numericals. This formula and this formula also. So for getting the minimum work, what we do is we just write the equation for two-stage combustion with perfect intercooling. We differentiate that equation with respect to P2 because we know that the varying quantity is P2, and for getting minimum work we equate the slope, we differentiate the slope and equate it to 0. So then after some simplification we get an equation like this: W is equal to 2 into n divided by n minus 1 P1 V1 into P3 divided by P1 the whole raised 1. Remember, this derivation is frequently asked in your university examinations. So please go through this derivation carefully and please write the equations along with me so that it will be more clear. Now, so far we covered all the topics regarding reciprocating compressor. We covered the working of single stage reciprocating air compressor. We derived the formula for work done for single stage reciprocating air compressor with clearance volume and without clearance volume. We derive the formula for overall volumetric efficiency, and we derive the formula for volumetric efficiency, and you understand the concept, what you mean by free air delivered and all those things. Then you derive the formula for, you studied about the multi-stage compression. Then we derived the formula for two-stage reciprocating compressor with perfect and without imperfect intercooling. Then we derived the formula for calculating the minimum work required for this case. Now, after that, we can conclude that in a reciprocating air compressor, since the parts are much heavier, the vibration encountered in reciprocating air compressor is greater. Then the mechanical efficiency. Mechanical efficiency is nothing but the ratio between the actual work, that means the polytropic work divided by the shaft work. That is the polytropic power divided by shaft power. You will get the mechanical efficiency. The mechanical efficiency is lower in reciprocating air compressor compared to rotary air compressor. The reason is it involves more several sliding and moving parts as compared to rotary compressor. Sliding and bearing members are more in case of reciprocating air compressor as compared to rotary compressor. And you know that the pressure ratio per stage is 5 to 8. When the pressure ratio is above 8, we go for multi-stage compression. And you know that the reciprocating compressor is commonly used for high pressure applications. One of the major drawback of reciprocating compressor is the flow is pulsating. It is not continuous. So for continuous supply and for medium pressure application, we are using rotary compressor. So the volume flow rate of rotary compressor is much better as compared to reciprocating air compressor. And finally, as the compression ratio increases, the combustion efficiency also increases, which is clear from the equation. So these are the conclusions and these are the topics which comes under reciprocating air compressor. In the upcoming videos, we will be doing some of the numericals regarding this. So just go through all the lectures regarding reciprocating air compressor, and in the upcoming videos we will be doing problems. So thank you for watching. Bye.